everyone and welcome to one of the important topic of the linear algebra which has a vast application called as singular value decomposition. Singular value decomposition. So in this video lecture we are going to study about its applications, then the basic concept as well as the problem on SVD. What we will solve one numerical on SVD, that is singular value decomposition. So singular value decomposition has many applications such as it is used in signal and image processing. The very first application which you find is in signal and image processing. Then we may have its application in polar decomposition of square matrices also. Polar decomposition of square matrices. Then it is also used in the data compression. Data compression. Then the next application which you find here is the least square approximation of vectors and data fitting. Approximation of vectors and data fitting. And many more application we have. So these are few of them. So what is singular value decomposition? So it's a decomposition process. Now what is mean by decomposition? Decomposition means dividing certain things into small parts. So what we are going to divide here? So we will be dealing with the data which we write in the form of matrix. Say matrix A, which is of size m by n. So in this singular value decomposition, we decompose any matrix A into a small parts, which are nothing but U, S and V. So any matrix A can be written as product of U, S and V transpose, where S is a matrix of S is a diagonal matrix. S is a diagonal matrix, M by N diagonal matrix. M by N diagonal matrix whose diagonal entries are non-negative, and this diagonal entries of S are called as the singular values of matrix A. Diagonal entries of S or diagonal elements of S are called singular values of A. So while evaluating the example, we'll see how to obtain the singular values of a matrix A. Then the column vectors. What is U and V? Again, note that the size of S must be same as the matrix A. If A is of order say 2 by 3, then S will also be of order 2 by 3. Then what is U? Here U is a left singular vector. U is a left singular vector of A. Left singular vector of A. And how do we obtain this? So this is obtained by getting the eigenvectors of m by n, m by m normalized matrix A into A transpose. So you will get by First obtaining eigenvalues of A into A transpose. Then corresponding to that we will find out eigenvectors and then it will be normalized. So U is nothing but the columns vector of U are nothing but eigenvector m by n symmetric matrix A into A transpose. Whereas V is called the right singular vector of A. And what are its entries? The entries are nothing but, so the columns of V we can say are the are eigenvectors of n by n symmetric matrix which is orthogonal that is A transpose into A. So the equation this A is equal to US into V transpose is called as the singular value decomposition of any matrix A. This is called as singular value decomposition of any matrix A. So remember here A is size of the matrix A is same as S. Then what will be the size of U? So size of U will be M by M. It's always a square matrix. Again what will be size of V? It is N by N. Again it's a square matrix. Okay, so you can how to find out the size. You can see here whatever will be the row here, number of row, that will be the size of U, whereas number of columns will be the order for V. Okay, and the rank of order of the matrix A is same as order of S. S is nothing but a diagonal matrix whose diagonal entries are non-negative. So this is what one has to remember. Again, how do we get U? So for this, we will take the help of A into A transpose. Whereas for evaluation of V, we will find out the normalized eigenvector of A transpose into A. Now, in many cases, the evaluation of the eigenvectors for A into A transpose and A transpose into A will become a tedious task. So, in this case, what we do? In this case, we use the uh, Gram-Smith orthogonalization process. In such cases, we use the Gram-Smith orthogonalization process if we know one of the matrix say U in order to obtain V or vice versa. So, how to find out say V if we know the matrix say U. So, if U is given, if suppose U is given, is known, then V will be given by, so the elements of V will be nothing but in the form V1, V2, V3 like this, depending upon what is the size of the matrix A. So it is given by a formula Vi is equal to A transpose into Ui upon sigma I. What is sigma I? These are nothing but singular values. Similarly, if V is known and we wish to find, if V is known, then how to obtain U? So elements of U will denote here by U1, U2 up to UN. So that is given by UI is equal to AVI upon sigma I. Now remember, for evaluation of U, you are going to take the help of the matrix A into A transpose. A into A transpose, right? Whereas for evaluation of V, we are going to take the help of A transpose into A. So all these basic concepts one has to remember. So let us start with the first example of the singular value decomposition. So find singular value decomposition of. So before this, let us see the examples of 2 marks where we are asked to find out just the singular values of the given matrix. So find the singular value of the matrix, say A is equal to, we have 1 1 0 1, then 0 0 0 1, then next we have 1 1 0 0. So you can see here the size of the matrix A is 4 by 4. So if we evaluate, it is nothing but 3 by 4, right? So A is of order 3 by 4. So we will find out the order or size for A transpose. So A transpose will be 4 by 3. Just interchanging rows and columns. So you will get the number of rows as here 4 and number of columns as 3. The size of the matrix A transpose is 4 by 3. So we will quickly find out what will be the size of A transpose into A as well as the A into A transpose. So you can see here the size of A into A transpose. Size of A into A transpose. So A is 3 by 4 whereas A transpose is 4 by 3. So removing this part, right? So what we have? 3 by 3. So size of A into A transpose is 3 by 3. Again, on the same line, we'll find out A transpose into A. A transpose is 4 by 3, whereas A is 3 by 4. So if we multiply them, so what we find, this will get removed, right? As per the multiplication of the matrix. So what you get? You get it as 4 by 4. So you can see here A transpose into A is of order 4 by 4, whereas A into A transpose is 3 by 7. So for the sake of computation process, we will consider a matrix A into A transpose as a new matrix which we denote by B. So let us take B as A into A transpose, which will be A in 3 by 3 matrix. Okay, so what will be 3 by 3 matrix? So first we will write A 1 1 0 1, then we have 0 0 0 1, next 1 1 0 0, this is A. Now into its transpose, so now we will have first row as a first column, so it is 1 1 0 1, next we have 0 0 0, then 1 again, third row will be a third column, so 1 1 0 0. Now let's multiply them. So what we find, I find here the 3 by 3 matrix which will be 3, 1, 2, right? Multiplying first row with the first column. So 1 into 1, 1, 1 into 1, again plus 1 and then 1 into 1, 3 I am getting here. So like this you know very well how to multiply two matrices. You can apply, you can use calculator also in order to multiply the matrices. So here I am getting like this. If you wish, you can refer my video on how to multiply matrices using calculator in the playlist. So here A into A transpose, which is our matrix B, is coming out to be 3 1 2 1 1 0 and 2 0 2 2 0 2. Now we will find out the matrix eigenvalue for this matrix. We'll find out the eigenvalue for this matrix. So we find eigenvalue for B. So that is here A into A transpose. So as per the definition, we need to first find out the characteristic equation. So characteristic equation is determinant of A into A transpose minus lambda I equal to 0, which is A into A transpose is B here. So what it is? So determinant of the elements of B are 3, 1, 2, 1, 1, 0 and 2, 0, 2. So corresponding to this matrix, we will find out the characteristic equation. So what it will be? 3 minus lambda, then we have 1, then 2, we have 1, 1 minus lambda, then 0, 2, 0 and 2 minus lambda equal to 0. Now we'll solve this characteristic equation. So we have the method. Since it is 3 by 3 matrix, so we will write lambda cube minus S1 lambda square plus S2 lambda minus determinant of A equal to 0. So here my matrix is not A, it's a matrix B. Here, this part is B. Okay, now simplifying this, so what is S1? S1 is sum of diagonal elements of B. What are the diagonal elements? 3, 1 and 2 are the diagonal elements. So how much it will come out to be? It will come out to be 6. Add them. So sum of the diagonal elements, that is 3 plus 1 plus 2. Right? So it is 6 lambda square. Then plus S2. S2 is nothing but the minors of diagonal elements and then their sum. So we'll take the minors of each diagonal element and we'll add them. That gives us the value of S2. For more detail, you can refer the video on evaluation of eigenvalue and eigenvector. So it comes out to be 6 lambda. Now again you can find out the value of this determinant using calculator. So you will get the value of determinant of this matrix as 0. So it's a 0 equal to 0. Now since we are getting the equation of degree 3, so we are expecting 3 eigenvalues for lambda, right? That is 3 values of lambda which are called eigenvalues. So if you solve this equation, again I will suggest you to use the calculator to solve this equation. So you will get this as 3 plus root 3, then 3 minus root 3, and the third value which you will get is 0. So out of the 3 values, the one value comes out to be 0. So 0 eigenvalues is not considered for as a singular value, right? So these are eigenvalues. We will arrange them in the descending order. So largest one must be put first. So we will denote lambda 1 is equal to 3 plus root 3. Among these three, lambda 1 is the largest one. Lambda 2 is equal to 3 minus root 3 and this is neglected. So since it being a 0. So these two are denoted by lambda 1 and lambda 2 and accordingly we will have the values of singular which we denote by sigma 1. So sigma 1 is as per definition it's under root of lambda 1 and sigma 2 is square root of lambda 2. So like this we get sigma 1 as under root of 3 plus root 3 and sigma 2 is equal to under root of 3 minus root 3. So remember whenever we get the eigenvalues as 0, that need not be counted as a singular value. So these are only this required singular values. So let's quickly see what we have done. So first of all, you need to decide which matrix you will be defining as B. Okay. So for this, we need the small size matrix. So we will evaluate quickly A into A transpose and A transpose into A, and whichever comes a matrix as of smaller size, that will be considered as B. Then for this B, we will find out the characteristic equation as per our usual process and we will find out its values which are called as eigenvalues. Then in the eigenvalues, we will not consider a 0 eigenvalues, right? For calling it as a singular values. So whenever you have zero eigenvalue, that will be neglected and remaining will be arranged in the descending order. So values are arranged. So I am getting here the sigma 1 is the largest one, sigma 2 is the smaller than that. So like this we get two singular values. So I hope the concept is clear to all. Now let's see one more example here. So find the singular values of a matrix, say 1 2 1 2, right? Or okay. So let us find this quickly. What we will do? So you can see here the matrix given here itself is a square matrix. So it's immaterial whether you consider A into A transpose or A into A transpose into A. Because as it is a square matrix, so both will come out to be of same size. So matrix given is 2 by 2, so both will come out to be a 2 by 2 matrix. So it is up to you which matrix you are going to consider here. So it's up to our wish which matrix we will consider. So let us quickly take here. I am taking A into A transpose. Remember, whatever will be the eigenvalues of A obtained, singular values obtained after evaluating A into A transpose will be similar as to that obtained for A transpose into A, since it's a square matrix. The matrix given is a square matrix. So let's find out A into A transpose. So here we get it as 1 2 1 2. So if we will take its transpose, so here we have 1 2, then 1 2. Let's simplify it quickly. So it's 1 into 1, then 2 into 2 4, 4 plus 2 5, 4 plus 1 5, then 1 into 1 1, 2 into 2 4. So again I am getting 5 here. Now 1 into 1, then 2 into 2, again it will be 5, 1 into 1, then 2 into 2, again it is 5, right? So A into A transpose is 5. So matrix B is A into A transpose. Now we'll find out the characteristic equation for matrix B. The characteristic equation for B is determinant of B minus lambda I equal to 0. So this implies determinant of 5 minus lambda. Again 5 minus lambda, 5 as it is here, equal to 0. So what this gives you? So it gives you 5 minus lambda whole square minus 25 equal to 0. You can either simplify this directly or you can use the formula. So what will be the formula to be used here? So we can use lambda square minus s1 lambda plus determinant of A equal to 0 as a shortcut method. Or you can go with the usual evaluation process also. That is what I have done here. Right. So what it gives you? So it gives you 25 minus lambda 10 lambda, then plus lambda square, and again 25 equal to 0. So it is 20 lambda square minus 10 lambda equal to 0. So this taking lambda common, so we get quickly here lambda equal to 0 and lambda equal to 10. In this way, again what we are observing that the eigenvalues are, one of the eigenvalues 0. So here that will be neglected. Therefore, only singular value here available is sigma 1, that is under root of lambda 1. Lambda 1 I am taking as non-zero eigenvalue, which is under root of 10, is the only singular value. So I hope this is clear to you all. So in the next video lecture, we shall see the singular value decomposition of a matrix. Thank you one and all for watching the video.